thank you for having me here. And since I talk about all my main line of research throughout the week in the summer school, if you haven't seen that, you should check it out. And so I'm going to just tell you some nice problem, fun problem that we are able to do some mild improvement from the trivial upper bound, and we are really interested in seeing what's the answer, or can you do some major improvement in the upper bound. So today I'm going to share you the topic about Oddtown modeling a composite number, and in particular we can get some lower order term saving from the trivial upper bound by using the linear algebraic method plus the Fourier method. So I'm going to share you how we use these two methods in the problem, and then probably you can think about that problem, and if you have some progress, please let me know. So let me start with the background. What is the Oddtown problem? So it's kind of the most basic classical one problem in the application of linear algebra in combinatorics. So the question goes as follows. You want to ask for the maximum possible size of a set family A, so that you should think of A as a collection of clubs in a town. So there's a town with n people under the following rule, so that any set A inside my family curly A is odd, and any intersection of two clubs, the common members of the two clubs, is 0 mod 2. So this holds for any A in my family, and this holds for any A which is not B in the family of clubs. So one easy construction to have many clubs is to just ask each individual to form a club themselves, so that in each club there's only one member, which is an odd number. That's good. And any intersection of two different clubs will be trivial, will be empty, so that the size of the intersection is even. So the construction is simply just take A to be all the singletons, in this case you get a set family of size n. And a nice application of linear algebra tells you this is the best you can do. So let me briefly remind you, how do you upper bound this? So I claim that for any set A, for any family A, you always have this inequality that the best you can do is n. And basically you should just identify all the set with its indicator vectors. So the proof is that you identify the sets in A with vectors say u1 to um. Let's assume there are m sets in f2 to the n. So for each entry, for the first entry, it's 0, meaning that the member is not inside this club, and if it is 1, meaning that the member is inside this club, and so on. So you can translate these two conditions in terms of inner products between these vectors, because if you take the inner product between two indicator vectors, the common one, the number of ones, common ones appears will be exactly the intersection, so that the inner product will be just the size of the intersection. So you have ui dot with ui, which is basically just A intersecting A, should be odd. And I'll just write non-zero because we're working in f2 to the n. And also we have ui dot uj is 0. That means these m vectors are orthogonal. So the size, the number of vectors, like all these vectors forms a basis. So the number of vectors is upper bounded by the dimension of the space. And indeed, this holds. All the argument holds if I replace 2 by p. So this is the same. Let me write it here. Okay, so one natural question is that if I replace this prime p by any composite number, what can I say? So let's say we have a composite number L which can be decomposed. The prime factorization is that p1 alpha 1 all the way up to p omega alpha omega. So let's say it has omega many prime vectors. Then what's the best construction and bound can we get? So again, the same construction still works because the size of each set and the intersection are 1 and 0 respectively. It doesn't matter which number you are taking modular with. So the construction still works, and indeed that's the best known construction. I think there is no construction known to beat this n by any number. Correct me if I'm wrong, but we didn't find any literature about this. And the trivial upper bound.
Did people ever try GPT generating
Right.
examples?
I should do that. I'll do that after this talk. Right. Remind me after the talk. Yes. Okay. So what trivial upper bound is that you can bound the number by omega times n, where omega is this number, the number of primes inside my prime factorization L. And the reason it's quite simple is that you can kind of collect all the vectors. Depends on their norm, like the dot product with itself, or like you just took, okay, you look at all the sets, and each set, since the set size is not 0 mod L, so it should be not 0 mod 1 of the p, and you just throw this set into the collection correspond to this p, and so that you can split your A into omega different sets, and prove using the mod p upper bound in each set. So I'm going to put.
But in a sense, you need the prime power, right? Alpha like the.
Yes. So.
But maybe same proof method just works for prime powers.
Good question. Yes.
You just look at the
Okay. So I had some typo in my show
p-added
notes.
valuation or something like that.
Yes. So I'll show you the proof how to get an improved bound when we're working with prime power. Well, the idea is that, okay, so let me, instead of proof, I say idea. Okay, never mind. So let's collect all the u inside A with u dot u, which is not 0. Mod p I alpha I.
So I guess you can replace f2 to the n by z to the n, and then look at the dyadic, the p-adic valuation.
Okay, so maybe let me skip this part and give you a improved upper bound, and this part will follow by that. So the idea is to take this one and try to argue an upper bound on the size AI. So by doing this, we can improve the upper bound. So kind of the trivial one is this one, right? And we can get some lower order term. Saying that if omega is at least 2, then the size of A is upper bounded by omega n minus 2 omega log n. plus some constant. And we can also show that, so this part is purely using linear algebra, playing with like prime powers. And we can also improve this saying that if L has at least 2 odd prime factors, then we get a tiny bit of saving by adding the epsilon here. And this, you can get this epsilon by doing some Fourier analysis. So, and for your record, the epsilon will be roughly the sum of 1 over pi squared. So it's really tiny and depends on pi. And indeed, the sum you sum over all but 1 odd prime factors. So that's why you need at least 2 odd prime factors.
Where is the 2 omega plus x?
Sorry?
2 omega plus
Oh, thank you. So, right, 2 omega plus epsilon. Yes, so this is the same 2 omega, but we get a small tiny bit of epsilons, and that epsilon will be roughly like 1 over p squared for each prime, for most of the primes. And basically the proof comes from 2 parts, as I mentioned. This is linear algebraic, and this comes from Fourier. So I will briefly mention how to, like I will go through how to do this linear algebraic part and briefly mention how to do the Fourier part. So before that, are there any questions? So let's get started. So for the linear algebraic part, let's assume di is the dimension of the span of pi under the field F, like under the characteristic pi, set of bi where I'm going to set here, the set bi is the complement of ai. A minus ai. So I'm going to look at the dimension of the span of bi over fpi. And I claim that the first claim is that the size of pi is upper bounded by 2 to the di. And this is indeed quite simple, because if you think about these bi, each one gives you an indicator vector. So let's call it v1 to vm. So let's say v1 to vm are vectors in bi. So this is bi. And this is n. So the length of each vector is n. And since we're assuming this is the dimension of bi in the span, so wait a second, I need. I'm getting slightly confused. For this definition, I need this to be p, but I should find it out. Okay. Sorry. Getting slightly confused by myself. Okay, never mind. Let's keep going. So for each bi, since the dimension is di, you can pick di many entries so that this is spanning. So, and you know these are 0, 1 entries. So since this part is spanning, every entry after that is determined by these di vectors. And you have, so let me write that in Word. So you have di vectors that span the column space, and I'm assuming that's the first di columns. So Vi is determined by these entries. So for each Vi, it is determined by this part. That means there are and you know these are different vectors. In particular, these vectors in the Di part will be different. Otherwise, since the rest part is determined by this part, you'll get if these two chunks are the same, then the whole vectors will be the same. So that means these are different, and you have Di many choices here. So you have at most 2 to the Di many choices for these chunks. So that means the size of Bi is upper bounded by 2 to the Di. So this is the first claim. And the second claim,
This is because it's a 0, 1 vector, right?
yes, it's a 0, 1 vector.
Any 0, 1 vector.
Yes.
Yes.
So you are crucial using the 0, 1 vector here. And later on you will see I'm going to replace this claim 1 by something slightly stronger, and you can use Fourier analysis. That's where Fourier goes into. It will improve that bound from this part. Okay, so for claim 2, I have Di less than or equal to n minus Ai over 2. Right. So let's set Ai to be k. Okay, let me talk about the intuition of this equality first. So it's you should think of these AI, what should I say? So if you look at the row space spanned by Bi, the dimension is Di, so it's kind of imposing Di many constraints. But on the other hand, you have Ai plus Bi many vectors that kind of satisfy this constraint. So you kind of have Ai plus Bi plus Di many vectors that is upper bounded by n. So that's why we have this quantitative bound here. Okay, so maybe let's go through a proof and see how do we really do the linear algebra here. So for convenience, I'm going to drop all indices I. So I'm setting D equals Di, P equals Pi, and also alpha equals alpha I. And I'm going to assume that the vector v1 to vd. So I'm just taking part of these vectors. I want to take D vectors that spans the row space. So I'm just taking part of those vectors. These are in Bi, and these are in span this space. So, and since Di is defined to be a dimension of this space, I can pick D vectors such that this hold. And let me also call the vectors in A by U1 to UK. Okay, so I'm going to play with these vectors and do some linear algebra to argue that if you do a dimension counting, you have if you count the dimension, you have this k plus 2d is at most n. That's our goal. So before talking about these equations and inner product, I want to. Okay, so let's first rewrite the condition, these conditions in terms of the inner product. So I have this vector u1 to uk, and these vectors v1 all the way to vd. So this part is my a, this part is my b, and I can talk about the inner product between these vectors with themselves. So from the Oddtown condition, we know that since we are defining AI so that this inner product is non-zero, so we have non-zero diagonal here in the first chunk, and the other inner products are zero because of the definition of Oddtown problem. And also for this VI, if you take the dot product between VI, this VI and UJ, you will get a zero because that also follows from the second line of the Oddtown problem. And this is zero as well because it's symmetry. And since these VI are in the collection so that the inner product is zero, so this chunk is zero as well. And everything I'm saying is under mod p to the alpha. Okay, so here I mean by star I mean it is non-zero. And what we can do, we can kind of clean up this matrix. And in particular, we can do some row operations, column operations. I can add one column to the other column. Adding VI to any other column doesn't harm, so it will keep preserving this inner product structure. So I can do row operations. Sorry, I can do row operations between V1 to Vd. So I can replace the matrix by a matrix of the following form. There's a question mark here. So I can do this because I pick VI to be a basis over mod in P, so I can get a 0 in the diagonal. So I can get 1 in diagonal and 0 elsewhere. And here we crucially use that VI are spanning over mod P, not P alpha. Okay. So this uses and another operator we can do is to replace UI by UI plus or minus some constant times VI, so Vj, right? Because if I add anything from here to here with some multiple, it won't change the inner product structure as well. So I can clean up. I can using all these ones to clean up everything here. That means it can become a matrix of the form where this is 0, this is identity, and I have d vectors, so this is ID, and let's call this one UI prime, and these VI prime. Okay, so what have we done? So let's look at the inner product between these UI prime and VI prime and see what's the relation between these new vectors by dropping the first d columns. So now we have a vector. We have vectors u1 prime to ud prime and uk prime and v1 prime to vk prime, and the width of this is n minus d, and in particular this part is k plus d. And if I do the inner product with itself, the new matrix I get, I could
Vd prime or Vk prime?
oh sorry, vd prime. And this is hard to remember. So since we're only removing the first chunk from V1 to V1 prime to Vd prime, because the first chunk in U part is 0, so it doesn't affect the inner products. So we get still the same star in the diagonal. And off diagonals are 0. These are also 0. And since we're subtracting 1 from each VI, so the diagonal will be -1s. And the off diagonal is still 0. And again, this is under mod in p to the alpha. Okay, so if the claim is false, then remember the claim is equivalent to say that d 2d plus is less than or equal to n minus k. I'm just rearranging term. Remember ai is k and di is d. So if the claim fails, we know that k plus d is greater than n minus d. That means this matrix is like this side is longer than this side. It's a rectangular matrix with this side longer. In particular, that means these vectors are linearly dependent over z. So u1 prime to uk prime and v1 prime to vd prime are linearly independent. So linearly dependent. Over z. So I should remark that all the operations I'm doing here, I'm actually doing this operation as over z. So for these multiply by c or subtract and add in things, I'm also always doing it over z. And you know that, like for the mod p to the alpha part, I can always add in or subtract things by. So how should I say that? Yeah. So basically, I'm just saying all the operations are over z. So this these vectors are living in z to the n, and this linear dependency is over z. Okay. So now we should get a contradiction by saying that if there is a non-trivial linear combination, then we kind of can argue that all of the coefficients should be 0. So let's say they admit a non-trivial linear combination a1 to a1 u1 prime all the way to ak uk prime equals b1 v1 prime plus all the way to bd vd prime. Let's suppose it has a linear combination over z. So, I mean, you could view this linear dependency over q and then just multiply. So you have like rational coefficient and multiply by a denominator, so you get an equation over z. So these are numbers over z. And moreover, you can assume the GCD, the greatest common divisor, is 1. Otherwise, you just divide by all the GCD. Okay. So the most basic trick is to just take dot product with each vector and use this property here to do the testing. So you see a lot of negative ones here, so probably we want to first dot product with the v. So if I take dot product with v, I know that the left hand side becomes 0 because the off diagonal terms are all 0. So we do dot with vi. So the left hand side will become 0 mod p to the alpha. And the right hand side would be exactly negative the vi term, negative bi mod p alpha. In particular, p divide, like bi is divisible by p. Okay, so let's keep doing. So we know that the right hand side has, all the bi has a lot of prime factors in p, like a lot of factors of p, each one is divisible by p to the alpha. So let's also try to do dot product with the left hand side using these ui's. So you dot with ui. So I guess the first thing is that you know a1 u1 prime plus dot 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 to a, that's the number, ak uk prime is 0 mod p to the alpha, because all the bi's are divisible by p to the alpha. And then you can dot with ui to this equation here. In particular, you know, this gives you something like ai times the star in the diagonal equals 0 mod p to the alpha. But since this star is non-zero, it means that the amount of p, the number of prime vectors of p inside this star, is less than alpha. In particular, this ai is divisible by p, just one copy of p. And so you know that p divided p is like all the a's are divisible by p, and all the b's are divisible by p as well. So you get a contradiction. So that's kind of how you play with this prime power. You first do some linear algebra, some operations over these like prime powers, and at some points you need to use the linear dependency over z to get some stronger assumption on the prime powers. So far so good? Okay. So next I'm going to briefly tell you how to do the Fourier part to get the tiny epsilon. And I think, although quantitatively that's not good, but I feel like the idea here is quite interesting. So let's see where can we get in with Fourier. So I'm going to tell you an improvement of claim 1, because you can see in claim 1 I'm not really using any information about these blocks are 0, 1 vectors. I just care about like these vectors are like as a column vectors are spanned by the first d columns, or like these entries are determined by the first d entries, but I didn't use anything about like they are 0, 1 vectors. So with that we can indeed get some tiny improvement. So well, I guess in claim 1, if we look at the same matrix, we know that all the rows are distinct, and for the columns, if I allow repeated columns, I luckily get one column that is 0, 1 vector. That is a 0, 1 vector. I can just copy that column many times, getting still 0, 1 vectors. So in order to argue something like saying like you cannot have too much combination that give you 0, 1 vectors, I need the columns to be also distinct. But after some cleanup steps, so after some reductions, we can reach the stage where there are many columns. So instead of calling this n, I'm going to call this number c, and many means that at least c columns are distinct. And you should think of c as a polynomial in n, so probably like n to the 0.4. And in this setting, I can prove something similar to claim 1. Saying that if I have a matrix, like the number of rows is m, the number of columns is c, and all the rows and columns are distinct. And also this is a 0, 1 matrix. So this is the matrix M. And again, let's assume D is the rank over P of the matrix M. So the same D as before. Then we can get an improved inequality. Oh, and I need one more technical assumptions. So I'm assuming 36 log of P and log are always in base 2. It's less than or equal to d. This is just a constant lower bound, so it's fine. And also d is upper bounded by 3 log c. If d is not too much compared with the log of c, then d should be kind of a lot compared with the log of m. So we can prove that. This is at least 1 plus 1 over 36 p squared times log 2 of m minus 2. So basically this says that if d will be either much larger than the exponential in c, c will be, okay, let me say that again. D will be much larger than the log of c, or d will be kind of larger than expected in the log of m. And in this situation, we know that, like, after the cleanup, c should be kind of large, should be something in n, and we can also assume bi is kind of large. It's also at least linear in n. So either way, like either this violated or this holds. Either way, we can argue that d is kind of larger than what we expected.
So you're saying that this is true for any zero matrix.
Yes. So
with
for
many
this
rows.
claim, for this claim one, you should forget anything about the Oddtown problem, and we have this lemma here. Okay, and indeed this is better than claim 1, right? So claim 1 indeed just give you d is at least log of m, anyhow. But we get this 1 over 36 p squared improvement, and that would be indeed the epsilon we got. Okay, so the idea is basically you should first play with the metrics a little bit and then do Fourier analysis. So I'm going to take part of the metrics. So remember we have m columns and m rows and c columns. I'm going to just pick d of them, that is spanning, and call in this new matrix L. So the rank of L is d. Then so since these rows are spanning, we know the others are linear combination of these d rows. So in particular, if I take a random linear combination of these rows, then I'm basically asking what's the probability that I hit this part. So what's the probability that I have a 0, 1 vector as an output, and the probability will give me a control on how many more rows I can have here. And indeed, the linear combination, after some cleanup, the linear combination of these rows to get these rows should be of 0, 1 coefficient. So indeed, I'm just looking at the following question, where I take a vector v, in 0, 1 to d uniformly at random. So the rows of m are of the form V transpose times L. So basically I'm just saying I'm taking a 0, 1 combination, and I want to understand how many ways I can again get another row that is 0, 1 coefficient. So the question is that what's the probability that, okay, I'm going to transpose a little bit, so I'm writing L transpose V. What's the probability that L transpose V is a 0, 1 vector? And since the number of entries is C, so this is 0, 1 to the C. So we want to upper bound this.
Why do you choose V as a 0, 1 vector? instead of arbitrary vector. When you span
Yeah.
a
So
row, there's a chance that you might need all kind of linear combinations.
yeah, so I'm hiding a little bit of cleanup here, but you just think of like if you already see a diagonal here, then the first the diagonal will tell you must pick 0, 1 coefficient here. Yeah, so here's the idea. I skipped some cleanup steps. Yeah.
Okay.
Thank you. And yeah, that's the reason I need 0, 1 to the d. So basically, I'm just asking like if I take a 0, 1 vector uniformly at random, what's the probability that you hit the linear combination give you a 0, 1 vector? Okay, and indeed we can prove the probabilistic form, like prove this. So replace that term 1 in terms of probabilistic form, saying that this is upper bounded by 3 times 2 to a negative d over 36p squared. So I guess this is the 10. And the idea of proving this is indeed apply Fourier transformation. So you set f of x to be the probability that rho transpose v hitting this particular vector x. And you look at the Fourier transform of this function. So it's defined to be just f of x times e to the negative 2 pi I times the inner product x with c over p. So this is the standard Fourier transform over fp. And remember that my matrix L, so I'm going to call my matrix L, this is R1 all the way to RD. And indeed you can, okay, I'm skipping the calculation, but you can use some standard Fourier transform trick to show that all the cases, all the Fourier coefficients are upper bounded by the following quantity, e to a negative pi squared times sigma of c over 2p squared. And where sigma of c is given by the following quantity, that you sum over j, sum the inner product of rj with this vector c and square it. And okay, so I'm going to skip another huge step, but after you do some cleanup of a matrix, you can always assume that the sigma is kind of small. So you can always assume that. So you can do this by passing to a submatrix. Rho prime inside L. Okay, sorry for skipping this step, but this is rather technical. And so, okay. I guess I'm not really demonstrating the idea really well here, but these are just standard. I promise these are standard Fourier calculation. And this step is technical, so I kind of skip both of them. But the final calculation will be just like using the Fourier transformation back. So you know f of x is the expectation of f of c hat, and e to the characteristic function. So you know the majority, like you know there are two terms. Oh, and I should mention this holds for any non-zero vector here. So you can have one part being the f hat of 0, plus the other part, oh sorry, this should be c, which is the Fourier coefficient with inside the absolute value. And you just upper bound this using the Fourier coefficient you get here. So this is kind of saying that the probability of hitting each vector, like you do the Fourier transform, all the Fourier coefficients are small, so that it's kind of split out, and so you hit the 0, 1 cube. The probability that you hit the 0, 0, 1 cube would not be too much. Okay, so let me end with the question that, do you believe it is the lower bound n or the upper bound omega n? Which side do you think it is closer? So I'm really curious about like any techniques that can get a linear improvement in either the lower bound or the upper bound. And thank you.
Thank you. Thank you for the interesting talk. Any questions?
So in the Fourier proof, where we use the division, say the exponential in
You mean which one? The
yeah,
this part?
yeah,
So I think it's in the cleanup step that you will need this one, and there is a construction you just take a O1 vector and take all the linear combinations. So let's say this side is D and all the linear combination here. This metric will satisfy the condition and kind of tells you that D should be roughly normalized by log C and log M and log C respectively. And this is 0. So it kind of says that the D cannot exceed, like should be normalized by these two things, and if it is large in one of the side, then it will be, so if it is too small in one of the side, then it should be kind of larger in the other side. Yeah, and for technical part, I think we use it in this cleanup step.
Can I ask something? What happens if P is 2? So when P is 2, then any linear combination falls into 0, 1 vector, right?
Yeah. So the whole thing doesn't work.
Right. So where the argument goes wrong? Or
So, good question. I think one part is that for these, yeah. So I'm saying the sigma should be small, and in that case, if you like, by small I mean if you look at the unit root on the circle, it will be not too close to the opposite side, the -1 part. But if you have p equals 2, it's always bouncing between -1 and 1, and some combinatorial argument that help us to show that sigma is small doesn't work there.
I see.
Yeah, so by small I mean this quantity will kind of closer, the real part will kind of closer to 1 than -1.
How tight is your claim 1 prime prime?
How tight? So the best construction we know is this one, and it has. How tight depends on what do you mean by how tight. We have a plot between like C and M, and the. Sorry, we have a plot. So you should normalize that by looking at log C over D versus log M over D, and we have a plot about these two quantities that this construction basically corresponds to a diagonal construction, and the improvement we can prove is kind of on the corner. There are some slackness, you can find that in our paper saying like about the tightness, but it's a little bit hard to describe because there are 3 parameters here. We have a plot about this.
Any other questions? Then if not, let's thank the speaker.